Hi, everyone. Thanks for joining me today. I'm Anastasia Lalamentik, and I'm a full-stack engineer at Kaleido based in Raleigh, North Carolina. And for those who may not be familiar with what we do, we are in the enterprise blockchain space, and we provide a platform for setting up private blockchains and digital assets. With the amount of interest around blockchain right now and its potential for growth in the upcoming years, I think it's important for all of us to be familiar with how blockchain works. So today, I'd like to show you how you can deploy your first smart contract on a live testnet with the latest tools that are available. And hopefully you'll walk away feeling that blockchain isn't actually as intimidating as it may seem. So without further ado, let's go over today's agenda. First, I'll mention the tools needed for you to accomplish the task. We'll then briefly discuss how smart contracts work and the basic concepts behind it. We'll then go through a quick overview of the Solidity programming language, and afterwards, we'll write a simple smart contract together and deploy it to a live testnet, live Ethereum test network. Lastly, we will test and interact with the smart contract. So here are some tools needed for this workshop. You can try to follow along or just listen for now and try to recreate the steps after today's talk. The GitHub link here has all the full details that you can follow. So first, you need a node development environment set up on your computer. You will then need to install Hardhat, which is an Ethereum development environment where you can compile smart contracts and deploy them to a live network. Next, you want to make sure that you have a Metamask wallet installed as a browser extension on Chrome or Firefox, and you can use the Goerli Faucet to fund your account. And 0.2 ETH should suffice for this demo. And lastly, you need an Infura account to sign up for to create a Goerli Network endpoint. I think you can also use Alchemy if you prefer that. And next, I will go over some basic concepts around smart contracts before we go through the actual demo. So how do smart contracts work and why do we want to use them? A smart contract is an agreement in the form of code which runs in a blockchain network. It requires at least two different parties involved, which makes it naturally inherit blockchain properties like being decentralized, trustless, transparent, and immutable. With smart contracts, we do not have to trust or rely on any single party involved in the system to do a certain thing. Smart contracts self-execute when specific conditions are met without having to rely on centralized authorities like banks or corporations that are prone to being slow and are not guaranteed to be trustworthy. Once the logic has been defined and deployed to the network, no malicious actors can modify it. Smart contracts are widely used to automate business, financial, and legal processes. They're also popular in the banking, government, and healthcare industries, just to name a few. So for example, in healthcare, smart contracts could automate payment processes and insurance claims, which may normally need to go through lawyers, business staffs, and could take months to process. This using smart contracts would help save time, costs, and also minimize opportunities for human error. Moreover, members in the healthcare blockchain network could work together to maintain a single source of truth for patient data, which will reduce the likeliness of fraud when it comes to insurance claims and also provide a better platform to track a patient's entire medical history. And just as a note, in enterprise use cases such as these, a private blockchain rather than a public network might be of interest so that only concerned parties can view and interact with the data. So let's now go through some basic smart contract concepts. First, we have the Ethereum Virtual Machine, which is the execution environment for smart contracts in Ethereum. And it contains the fundamental consensus mechanism. So smart contracts are compiled from a high-level language into bytecode so that the EVM can understand it. The EVM behaves like a mathematical function. Given an input, it produces a deterministic output. Every node on the Ethereum network launches an EVM instance, and this ensures that all participating nodes agree on the execution of the same instructions or code. And since a blockchain network involves thousands of computers all over the world that are mining transactions, gas fees are required to process them. If gas is insufficient, then the contract will be suspended. Gas fees could vary based on how busy the network is. If there is a high number of transactions, for example, the average gas price would rise and vice versa. Gas fees are needed to prevent attacks that can slow down the entire network. Next, we have block explorers. Block explorers are commonly used to view information about blocks, transactions, and balances in a particular blockchain network. And we'll see this later on in our demo. So block explorers, they show addresses of smart contracts and Ethereum accounts, which are represented by a 42-character hexadecimal address, such as this one. And lastly, we have ABIs, or application binary interfaces. ABIs defines the methods and variables that are available to interact with in a smart contract. Since smart contracts are converted into bytecode before they get deployed to the blockchain, and bytecode isn't quite human-friendly to read, the ABI provides a standardized way for us to know what operations and interactions we can initiate with them from any programming language. Basically, it allows communication between a web application written in a high-level language like JavaScript and the bytecode that the Ethereum Virtual Machine understands. So this is a quick glimpse into what bytecode looks like after code from a high-level smart contract development language like Solidity gets compiled. And on the right side here, we also see the corresponding ABI code, ABI generated from that small piece of smart contract. It's in a JSON format that is readable. There's only one function here, but as you can see, this JSON contains an array that describes this whole smart contract. So if we had a more complex smart contract, there could be other types like constructors and events on top of functions. And I also want to touch on gas fees and the different subunits of Ether. You can see that a GUA is being used to display gas prices in a more readable way on the Block Explorer Etherscan. So moving on, let's get familiar with the Solidity programming language. So Solidity is a high-level programming language highly influenced by Python, C++, and JavaScript. It is specifically designed for implementing smart contracts, and it runs on the Ethereum Virtual Machine. So here's an example of a simple storage smart contract to read and to write an unsigned integer value to the blockchain. So when you first write a Solidity smart contract, you want to start with defining the Solidity compiler version that you want to use. So in this example, the code states that this contract is compatible with compilers of version greater than or equal to 0.4.0, but less than version 0.6.0. So this needs to be defined because future versions of the compiler may contain changes that are not compatible with this code. So after specifying the version pragma here, we open the code with the contract keyword and followed by the smart contract name. We can then start writing the logic in it. We start by defining the state variables needed and then writing the different function declarations as we normally would in other programming languages. In Solidity, supported types include signed and unsigned integers, Boolean values, addresses, enums, and bytes. You can also specify the function visibility type in Solidity, which determines what can be interacted with publicly on the blockchain versus what needs to stay within the context of the current contract. There are also pure and view functions. So view functions ensure that they will not modify the state. So getter functions are by default view functions. Pure functions should not modify or read from the state. So it's suitable for functions that take in parameters to feed into mathematical equations or for string manipulation. Next, let's go through a list of global variables that are made public in Solidity. So Solidity gives us access to this list of global variables which provide information about the blockchain and the transaction properties. In our demo today, we will be using message.sender and block timestamp in our smart contract logic. So without further ado, let's actually write and deploy a smart contract together. I'm going to switch to sharing my entire screen now. So let's do that. I have a couple of questions, it looks like. Oh, no, just notes. Cool. Awesome. I'll share my entire screen now. Great. Cool. So here I have a project that I'm going to name demo 1. And inside of demo 1, I'm going to initialize an npm project. So I'm going to execute this command. And now I have an npm project in this folder. Next, I have Hardhat already installed. I have everything installed on my machine. But I also have the instructions here if you need to go through them. So I installed Hardhat by executing this command. And I also prepared some of the values that I would need later on earlier before this demo. So I got my Metamask wallet set up for the Goerli test network. I funded my account with some Goerli ETH. I also set up my network endpoint inside of Infura. And I also set up these different environment variables that I will need when I to deploy the smart contract into the live testnet, the Goerli testnet. So just a note, I've already set up all these things that are highlighted inside of the GitHub link. So I'm going to go back here. I'm inside of
Anastasia, would you mind making your terminal a little larger?
Oh, yep. I mean, I don't mind at all. Is that better?
Yeah, that's great.
Okay, cool. All right, so now I'm inside of the demo 1 folder and I want to initialize a Hardhat project. So I'm going to type in npx Hardhat. It's gonna start initializing and installing some stuff into this folder. And I'm also actually going to show what's here inside of the demo one folder. So what do you want to do? I want to create a JavaScript project, and I'm just pressing enter here, going with the default values. And as you can see inside of my Visual Studio Code, initializing a Hardhat project, created all these different templates that are really useful to get started with deploying your smart contract to a live network. So let's see if that's done. Great, so the project is created. And the next thing I want to do now is to actually write a smart contract together with you inside of Ethereum Remix. So just to keep things simple, I'm going to pretty much write a slight modification of the smart contract that has been provided by Hardhat. So this lock smart contract, what it does is it takes a time in the future, and it takes in also an ETH value to keep to lock inside of the smart contract. And the owner of the smart contract can unlock it once the unlock time specified has passed. And I'm going to write a smart contract that's pretty much the same thing, but each time the user or the owner of this contract withdraws, calls the withdrawal function, it only withdraws half of the current balance instead of the full balance. So let's switch over to Ethereum Remix. Ethereum Remix is a really popular tool for people to start writing Solidity smart contracts without having to do a lot of local setup on their machine. It's a really nice tool, especially since right off the bat, it comes with all these really helpful examples on with varying complexities. So you have storage, so where it just stores and retrieves, or it provides a way for you to get and retrieve an unsigned integer from the blockchain. And then there's also the owner contract, where, as you can see, it's a little bit more complicated. There are events, there's logs, there's conditions that need to be met. And then there's also the ballot Solidity smart contract example, where you can, it's a voting contract. And as you can see here, there's maps that are being used, there's for loops. And the reason why I'm showing this is just to show you guys that there are really helpful resources out there where if you don't know where to start, you can start by, trying to understand these examples and building your own smart contract off of these examples, because they're really helpful. Personally, I find that's the case. So yeah, that's the reason why I wanted to show Ethereum Remix. And also I want to show this auto compilation feature that's provided here. It's really helpful when you're writing a smart contract. It detects errors for you. And so let's see how all this is helpful. So I'm going to write a new smart contract called lock and withdraw half .sol. And the first thing, as we've discussed before, we need to specify the version pragma. So I'm just going to copy paste from the other examples to make things simpler. And so we start with the contract keyword, and then the name of the smart contract itself. And so that's the wrapper for our smart contract. And then we can start defining the different state variables that we want to track. So the first thing we need to know is who owns this contract. So it's going to be an address that is public, and I'm going to say that this is the name this variable owner. And since we're going to make some transactions or like transfer funds in and out of the smart contract, we're gonna make this address a payable type, so that we can call functions like transfer or send to this address. And then the other thing that I want to keep track of is the unlock time. The unlock time is, yeah, when the owner can start getting funds from this smart contract, when their funds will be released. So now we have the constructor, and the constructor takes in the unlock time. And we're also going to make this a payable contract, since we're dealing with ETH coming in and out of it. And then the next thing that we want to do is to make sure that, so we want to do some checks, right? We want to make sure that some conditions are met before we can move on to the next steps. So for things to make sense, we need the unlock time to be in the future, because otherwise it just doesn't really make sense. So the unlock time needs to be larger or in the future, so larger than the block.timestamp. And block.timestamp is pretty much the current time whenever this piece of code is being called. And then the next parameter is actually the error message that the user would see whenever this condition is not met. So here we can say that unlock time has to be in the future. And if that is good, then we can move on and we can start assigning our local variable to the unlock time that is passed through the constructor here. And then the owner, I would also want to assign it to the message.sender. So whoever's calling this constructor, I want to set that address as the owner of the contract. And as you can see here, there's an error, expected semicolon, but got public. Oh, okay. I actually switched around the decisions of the variable here and the variable type. So that's really handy. That's where the autocompile functionality comes in handy. It detects little mistakes like that for you, which is really nice. And I just want to check that I'm doing everything right so far. So address payable public owner, uint public unlock time. Cool. So this all looks right. The next thing that I want to do is to actually write the function withdraw half. And I want to also make this function public. So the first thing that we need to make sure is that the owner is, or the sender of this, whoever's calling this function is the actual owner of the smart contract. And if that's not the case, then we can send a message saying that only the smart contract owner can withdraw funds. And then the other thing that we need to make sure is that the current time is already past the unlock time. So this needs to be bigger than the unlock time. And if that's not the case, then we'll say that funds are not available yet. Please wait. Let's wait longer. Okay. And if both these conditions are met, then we're good to actually have the smart contract release half of whatever the current amount that is stored in it to the owner. So here's the other thing that I want to introduce. I want to introduce events. So whenever things like this occur, we want to obviously keep track of it. So one thing you can do is to specify an event class here. So event withdrawal. And then there are two things that I'm concerned about when a withdrawal event happens. So first of all, I want to know how much is being taken out. So amount. And then I also am concerned with when this event happened. So now we have this. And now we're ready to actually emit the event. So we have the address of this contract, and there's we want to refer to the balance. And then we want to divide it by 2. And we also want to know, we also want to supply the block timestamp, which is the current time, into the event. And then the last thing we need to do is to send the actual value to the user. So it's owner.transfer. So we're going to transfer this to the owner. And yeah, this is pretty much the smart contract. So I'm going to copy this over to my VS Code and get ready to deploy it to the Goerli testnet. So coming back here, I am going to create the lock and withdraw half. Smart contract, and I'm going to copy over what I wrote here. And just for the sake of simplicity, since we're going to use the provided deploy script supplied by Hardhat, I'm just going to make the version and the licensing the same as the example smart contract. And I also just want to make sure that I'm not missing anything. So let me just quickly compare the two smart contracts. So we have format here. So we have the unlock time and the public owner. We have the event. Yep, everything looks good. Oh, I guess this could be greater than or equal to. Yep, and we're dividing by half here since we're just withdrawing half. But this all looks good. So now I want to deploy the smart contract. So the first thing we want to do is to compile the smart contract, right? So we're going to execute this command, npx hardhat compile. And what this does is it'll generate files like the ABI, which we talked about earlier. Here's the ABI and the bytecode that was generated by the whole compile command. And the next thing we want to do is we want to go to deploy. And here, the example script is locking the funds for 1 year, but we're not going to wait 1 year. So let's change this to 3 minutes and make that 3 times 60 seconds. So copy that over here too. And then we're just going to use a small amount since it takes some time to mine the Goerli ETH. So I'm just going to do 0.1 as the locked amount. And the contract is lock and withdraw half. And let's see what else. So yeah, so here, inside of the deploy parameters, we supply the unlock time and also the value of the ETH that we want to lock inside of the smart contract. So I think all this looks good. The next thing we need to configure is this Hardhat configuration file. So we're going to define the networks. So I'm going to specify the URL for the Goerli network. This will be the Infura Goerli URL. Actually, let me make sure that I have the correct one. So Infura URL Goerli and private key Goerli. So I have these two environment variables already set. And if you're trying to set these variables, this is the command that you would run. And for the private key inside of Metamask, or the private key Goerli here, you can get that from your Metamask wallet. I'm gonna show you the button to export the private key, but obviously I'm not going to share that on screen. It's really important for you when you're developing these kinds of applications, blockchain applications, to be cognizant of how you're storing these credentials, as if somebody else has access to it, they can take your ETH, they can execute transactions on your behalf, and just, I don't know, if there are any bad actors, you could be in trouble. So just be mindful of these values when you're developing. Don't commit these values into your GitHub repo. Make sure you're setting them as environment variables in your local machine, or just proper secrets management if you are going to deploy this stuff. So what's the other thing that I need? So I also need to specify the accounts. So I have, what's the other one? Private key Goerli. Okay. So yep, so that's all I need for this.
Anastasia, do you need to change the Goerli URL? Isn't it Infura URL Goerli?
Oh yeah, thank you for that. Kind of escaped my mind, even though I did notice it earlier. Thanks for that. Cool. Awesome. So now, all right, so now we're ready to actually deploy this to the Goerli testnet. And I'm going to have to look at my cheat sheet here if I don't exactly remember. So it's npx hardhat run scripts deploy JS, and then we're going to specify the network as Goerli. So here you can actually have like mainnet, you can have other test nets, Ropsten, whatever, whatever Ethereum live network you're interested in. Just make sure the URL and account is different for each of them. So coming back here, I'm going to run this and hopefully everything will work. This should spit out a contract address that I'll be able to look up inside of the Block Explorer. see. Right. Cool. So lock with 0.1 ETH and unlock timestamp. By the way, this unlock timestamp is just a Unix timestamp. So here you can convert it, and so my funds will be released at 10:40. It's 10:38 now. So in 2 minutes, I'll be able to start withdrawing stuff from my smart contract. And I can also take this address, paste it here. And as you can see, 40 seconds ago, contract creation, it's on a live test net. Like you can actually go to this address and see the same thing. And the balance is 0.1 Ether as we've defined in the deploy script. So that's pretty cool. I'm going to actually, let's see, what's the next thing that I can do here? Oh, right. So I'm going to verify and publish my contract source code so that I can interact with it from the Etherscan website. But actually, before that, I'm going to show a script here that I will use to interact with the smart contract from a like JavaScript, a Node application. So interact.js, I'm going to copy this. I'm going to change the smart contract address to this one. And let's see what happens when I execute the script. Oh, right. I haven't actually installed all these different packages that are needed. So I need Web3 and Truffle. Web3 and Truffle HD wallet provider. So I'm gonna let that execute, and I'm gonna come back here and actually verify and publish my contract source code like I was going to. Solidity single file, and the compiler version was 0.817, and I specified no license here. So let's see, continue. Here's where I'm going to go to my ABI and copy this whole array. So this is the compiled contract, right? So there's the ABI property here that is an array that I'm going to take and paste here. I'm not a robot, verify and publish. Interesting. Okay. Contract address. Oh, sorry. I'm not supposed to. I've copied the wrong thing. I'm supposed to copy the actual smart contract code here that we wrote together. So let me do that and try to verify and publish this one more time. So yeah, the Solidity contract code is just this high level Solidity code. So now we have that successfully generating the bytecode and the contract ABI. So this is the exact same thing as what I was trying to copy here. The bytecode is also the same, 0x60806. Yeah, so let's go back to our contract address, contract here. And as you can see, what that did was that when you go to this tab, the contract tab here, you get a green check mark saying that the contract source has been verified. And you, let's see, you can also interact with the smart contract now. So you can read the values inside of the smart contract. The owner is me. This is the same, like 0x5FE, that's me. The unlock time is the same one that we looked up inside of the Unix timestamp converter here. And now here comes the interesting part, which is actually withdrawing value from the smart contract. So just as a, just to show you, here's my initial balance, 0.7693. And I want to call this function, but of course I need to connect to my wallet first. So now I'm connected to my wallet and my balance is 7693, and I want to withdraw half of the amount that is in this contract. I'm going to say confirm, and here it says that the transaction is pending, but there's also an option to speed the transaction up by paying more in terms of gas fees. So I'm going to do that. I'm going to select high speed, so I'll just pay more to get a higher speed transaction. So this is 7693, and hopefully it will update soon to nice. Okay, so I just withdrew 0.05 and added it to my account balance here, and the successful transaction can also be found here. There's the gas price, there's the gas fees, and the function. And then let's see, I'm going to refresh this page. The balance of the contract has been reduced to 0.05. And when you go to the events tab, it also shows you that the withdrawal call was called, and the amount is this, and the timestamp is also shown there. So 10:44:48, yep, that checks out. So yeah, that's pretty much yeah, that's pretty much it. Like we wrote the smart contract together, put it on a live test net. It's the same thing if you wanted to do the same thing inside of the Ethereum mainnet. You just need like way more expensive ETH, and you need to be really, really careful with the code because, you know, any mistakes could be very costly. So I think it's always a good protocol to just go through test nets when you're developing your smart contract. Make sure everything works properly before, like, you know, putting in real ETH and doing real transactions with inside of the mainnet. I'm actually going to do this another time just to show that the code's working properly, and it only takes out half of. I'm actually not going to do it through here. So I also have another script that I just uploaded to the GitHub before this workshop. So this is how you would actually connect to the smart contract from a node, just a regular node app. So let's say you want to build a Web3 application where you have a UI that when you press a button, let's say you have like a piggy bank UI or picture, and when you click on it, it withdraws funds from the blockchain smart contract. This is what you would need. You would need the Web3 package, you would need a Truffle HD wallet provider package, and then it's really simple. As you can see, you need the smart contract ABI. So here I'm just connecting to the this file that has the ABI, and I'm actually yeah, referring to the ABI here. You can also just manually copy that array part and then just paste it here without having to import the file, since these are all git ignored anyways. So if you're trying to execute the script from my GitHub, this part might be confusing because this wouldn't exist in my GitHub, but that's just a note that I want to make. And then all these environment variables, this is your wallet address for the Goerli wallet, Goerli account. So for me, that's this value, which I've also set inside of as environment variables in my local development environment. And you need the private key as well, the same one that we used in the configuration file. Infura URL is also the same thing here. So you just need this additional URL. And then the other thing that you need to change is the smart contract address. So yeah, I already changed the contract address to be the one that we just deployed together. And so pretty much what this does is it initializes the provider, taking in your private key and the network endpoint, and initializing a Web3 instance with that information. And then the contract, it takes in the ABI of the lock and withdraw half smart contract, and then also takes in the address. And here's how you can call like different things. These are just some examples, but you can go through the Web3 NPM package documentation to see like the full list and the full capabilities of the package. But here, this is how you would get the owner of the, so these two things are just the state variables that we defined initially, and they are accessible as methods through this Web3 package. So owner and unlock time, we're just reading those values. I'm just converting the unlock time to a human readable form here. And then I also printed out the initial wallet balance. And here is where the interesting stuff happens. I'm actually withdrawing half here, and I'm making sure that I'm also, there's someone who just raised their hand.
Keep going, Anastasia.
I'll just keep going. Okay.
Yeah, we'll grab the questions at the end.
All right, cool. Yeah, so here's where we are actually calling that method that we define in the smart contract. And we also need to specify who is sending this call to make sure that it's validated, or is the owner of the smart contract. And so I'm just going to execute this script. And yeah, converting to ETH, like I touched on before, Gwei is like 10/18. To get ETH, you have to divide the Gwei by 10 to the 18th. So let's see, let's actually execute the script now. So now I have 0.8166 Goerli ETH, and inside of the contract is 0.05 ETH. So here I want to say node interact.js. All right, so it shows me the initial wallet balance, which was 0.8166. And then it'll come back with the receipt of a successful transaction. So final wallet balance 0.83. Also updated here 0.83. And if I refresh my contract here, the balance is now halved to 0.025. And you can see the block number, you can see the transaction hash, all this good stuff is returned by the receipt of the transaction. So yeah, just imagine like this was pretty easy. We got like a Web3 app without the UI running in like an hour. So yeah, hopefully you learn a lot from this workshop. That's all I have today. All of this is accessible inside of my GitHub repo here, deploy smart contract. So if you want to try it, and if you have any questions, feel free to yeah, send me an email, or yeah, connect with me on LinkedIn and just ask questions there if there's any more follow-up questions. But yeah, I think we have some time. So it's like 7 minutes for Q&A. Okay, hold on. Whoa, I have not seen any of these earlier.
Yeah, these all just came in, so I can help Olga. So Olga, you'll need to extend kind of your application a little bit. The question was, why can't I see the metadata or the actual NFT asset in MetaMask? Where does the metadata live? That's the question, right? That's the nature of an NFT, right? It has a URI where the actual rich data lives. So you'll need to create an application where you can call your IPFS endpoint, for example, right? We provide that on Kaleido, and you can actually do a download or a read operation and expose the metadata that's associated with that NFT. So it's a bit more, it's not quite as simple as just saying, hey, here's a balance, here's a fungible balance inside of MetaMask. You can see the indexes and you can see the tokens that you own, but you need to actually create, a Reactful, Angular application front end where you can expose that metadata. Happy to talk through that offline and give you some examples, and know that you've seen that you sent an email to us as well. So we'll respond to that. For Lissandro, he asked about Firefly. There's a lot of similarities with what Anastasia showed and sort of how Firefly reacts. Specifically, what Anastasia showed was two really important things. The first is the sort of manufacturing of the smart contract, and she took you through some syntax examples and also Remix, which is interactive development environment with a linter as well. So Remix is a really awesome utility to make sure that you have proper smart contract code, that your syntax is appropriate, that your variables, global and public, et cetera, are appropriate, and that it compiles. Once it compiles, you can then use something like Truffle or Hardhat to actually write unit tests against the functions that are available in your smart contract. And Hardhat and Truffle are more than just unit testing utilities. They're also client drivers as well. So they can be used to drive, JavaScript application logic, the scripts Anastasia was showing, but also to, of course, deploy and invoke your smart contract. For Firefly, it's a little different, Lissandro, because Firefly is a brain, if you remember. Firefly itself is not a blockchain. So what you're doing is you're teaching Firefly about important things. Specifically, you're teaching Firefly about that ABI that Anastasia spoke about. Once you teach Firefly about the ABI, then you just get those really simple REST API endpoints that you can use to speak to the smart contract. I'd also like to mention, Anastasia spent most of the time focused on kind of the public Ethereum testnets. Kaleido also provides a lot of node as a service and blockchain infrastructure. So if you wanted to sort of remove any transaction fees and gas from the equation, then you could target a gas-free consortia type Kaleido sidechain running Geth or Quorum or Besu or Polygon Edge. But all of the mechanics that she's gone through here in terms of how to generate a smart contract, how to test the functions using Hardhat, those are all still, really, really appropriate precursors. And then it's just a question of what network do you want to deploy the smart contract on. Now, Kaleido at this point in time today, very much out of the box in terms of software as a service, very much operating in the enterprise permissioned blockchain space. So the private Ethereum variants I mentioned, Hyperledger Fabric, and R3 Corda. We will shortly be adding public functionality directly into the self-serve Kaleido experience, But if your company has requirements for, speaking to a public EVM compatible network, just reach out to us. We'll put contact information in the chat, and we can help you stand up some bespoke infrastructure to speak to those networks. And you can also utilize kind of our Web3 gateway, our Web3 engine, which is Hyperledger Firefly, to really accelerate and simplify interaction with those networks as well. Olga's another question: what can I tokenize? So you can put whatever you want into IPFS, right? The metadata for an NFT, for a non-fungible digital asset, can actually live wherever you want it to live. Typically, right, these are public assets, so they're going to be on IPFS, public network or a private network, but those nodes are agnostic to the data, the payload that you send to them. So it could be an image, it could be a video, it could be a PDF, it could be a JSON object, it could be a .text file. That's simple. All right, I'll let you answer Shane's question, Anastasia, if you've been able to read that one around structs and variables.
Yeah, to be honest, I'm not really sure. I haven't had to write super complex smart contracts yet, but I'm definitely going to find out after this.
Yeah, and so Shane, I mean, I imagine you're very familiar with kind of like Open Zeppelin. So that's a community that we're big fans of, just in terms of kind of battle hardened templates that have, examples of pretty sophisticated, smart contract syntax, whether it's dependencies, whether it's escrows, whether it's, something that, Anastasia showed today with sort of locking data or locking value into the contract and attributing timers or, different unlocking parameters right there. But we're happy to take that one offline and, talk in more detail about the APIs that I alluded to, or through just a classic Web3 library like Web3 JavaScript or, Truffle, Hardhat, one of these sort of Web3 client libraries and test suites right there. Advantages of Hardhat versus Truffle from State Street, from Ganji. I'd say it's really just a preference. Fundamentally, they're doing the same thing. Our developers have sort of, let Anastasia speak to that, but we've seen sort of an affinity for Hardhat over Truffle, just in terms of user experience, in terms of depth, in terms of simplicity. So, we're not here to denigrate Truffle by any stretch. It's really just sort of a meritocracy in the dev community of, which tooling is the most powerful and which tooling is the easiest. And as you can see, Hardhat provides you with a really, really easy roadmap. Truffle does have some nice things in terms of like Truffle boxes with sort of, existing source code and existing JavaScript that can talk to them. So I'm not sure what depth of examples Hardhat has. So maybe that's one advocation for Truffle, but they're both really awesome frameworks and utilities. And they're really fantastic for, sort of just testing out all the functions that you've written inside of that smart contract. Can you write a similar Hyperledger Fabric version of this short project? That's an awesome idea, Pete. So yes, we're doing a lot of work to extend sort of the Fabric capabilities on Kaleido, including adding private data collections, CouchDB, et cetera. But similar to Fabric, what we also have, right now we're talking about the world of chain code, we give you the same easy button that you have in Ethereum for Fabric, meaning if you bring a good piece of chain code into the platform, now you no longer need to use the Node.js Fabric SDK or the Go SDK. You get to speak REST to that smart contract, and the Firefly/Kaleido engine, right? It's called Fab Connect. It'll actually do the heavy lifting for Fabric, things like collecting those endorsement signatures and actually proxying that payload up to the ordering service. So similar to how we make life really easy for Ethereum, which Anastasia didn't show today, she showed more of a public approach. We make life really, really easy for Fabric. So yes, we'll absolutely show that as well. Let's see. Hard to get Geth through faucets. How much ETH would I need to test, or are there other faucets? Anastasia already answered that one for Aldrin. Fantastic. All right, still scrolling through these. Feel free to drop if folks have other meetings or calls. I just don't want to. I want to acknowledge all the questions. Does Kaleido deploy nodes locally or in AWS, Azure? Yes, all of the above. So Kaleido provides you with a SOC 2 Type 2 compliant, ISO 27K compliant platform where we will fully manage, fully host, give you HADR, auto scaling out of the box for all of your private blockchain infrastructure. So this could be Ethereum, this could be Fabric, this could be R3 Corda, this could be, you know, even your application tier for that matter. And out of the box, we do provide fully managed support across 4 regions on AWS and 2 regions on Azure. So you have a global footprint. We also support cross-cloud compatibility. So you're not locked into a specific cloud provider or a specific region, meaning if you have a decentralized consortium model network, company A is an Azure shop, company B is an AWS shop, they can each run their nodes on that cloud provider and connect back into their existing cloud estate and their existing cloud infrastructure. And we also provide a service called Kaleido Private Stack, which is a bit of opening Pandora's box just in terms of the responsibility that you take on, but this will allow you to run a containerized piece of Kaleido software, a node image, a tunneler, and a little API microservice agent in any cloud or mainframe of your choice. So if you guys, if we have, I know we have a few banks on the call, if you have InfoSec requirements to say, hey, my blockchain nodes data, that level database, or the keys on my blockchain node, those have to be on this Z machine, this mainframe, and it has to be behind our DMZ, then that's possible as well. That just adds complexity to the orchestration of the network, because now you're not just an application developer, right, building out something for your end users. Now you're also a system admin of that blockchain node and those other resources. So, you need some Kubernetes chops, and you need to sort of understand how to create your own high availability. But yes, that's absolutely possible. Just a bunch of thank yous from everyone. Yeah, Jim, it's agnostic to the cloud that you provided on. So Jim says GCP, IBM cloud, where can we run it? If you use private stack, you can run it wherever the heck you need to run it. We advocate very strongly for what I like to call the crawl, walk, run model, where just let Kaleido do all the heavy lifting for you. Let us do the thing that we're really good at, which is running chains, running enterprise grade blockchains, and you get your application right, okay? Get your chain code, get your Solidity, right? Build a beautiful user interface on top of it, answer the hard questions you have around key management. Once your application is built and you're starting to be able to quantify the ROI and the value of the application, then let's sort of go into the conversation of moving one of the nodes off of Kaleido and into your own, GCP, IBM cloud, mainframe environment right there. It's sort of the logical path to take versus, going inside out and sort of suffocating yourselves with node running and really esoteric pieces of the technology. And then, maybe you forget to actually, focus on the application tier and the value that you, came to Web3 in the first place for. So I'm going to put 2 additional URLs in here. If you have any commercial or technical questions, just reach out to us at sales.kaleido.io. If you want to get, a little lower technical or use case specific, just reach out to me directly, and we can talk about architecture, talk about, and anything that makes sense. And yes, Jim, we'll email the chat text. We will send out the recording of this wonderful session led by Anastasia, and we'll also include some additional resources, case studies, documentation, code examples, etc. But we're an open book here. We're very receptive to conversations of all shapes and sizes. So please don't be shy if there's anything we can help you with, no matter what point of the Web3 journey that you're on. So thanks to everyone for staying a few minutes over. Huge thanks to Anastasia. That was a rock star session. And like I said, if there's anything we can do to help, just reach out. And I wish everyone a lovely remainder of their day, whatever time it is.
Thanks, everybody.